So welcome to today's explainer. We're tackling something absolutely crucial: motion, the literal building blocks of physics. By the end of this journey, I promise you, foundational physics won't seem scary at all. Actually, it's going to make perfect logical sense. We're going to strip away all that confusion and look strictly at what the concepts really mean. Okay, let's dive into our roadmap for today. We'll hit the basics of physical quantities, motion and rest explained, distance versus displacement, understanding speed and velocity, uniform versus non-uniform motion, and finally, an introduction to acceleration. Starting right at the top with Section 1, Basics of Physical Quantities. Listen, every single journey in physics starts with a physical quantity, which is honestly just anything you can measure. Look at the pen on your desk right now. You can measure its length, or you can measure its mass. Say it's 10 grams. That makes it a physical quantity. But what about human feelings? You can't exactly say, I feel 10 kilograms of love for you, or I have 40 kilos of anger. Emotions just cannot be measured on a scale, so they aren't physical quantities. Physics only deals with what can be concretely measured. Now, within all these measurable things, we actually have two separate buckets: scalars and vectors. A scalar quantity, it just has magnitude, which is really just a fancy word for a number. For example, if I hand you an apple and say, this is 50 grams, well, that's the whole shebang. You don't need to know if it's 50 grams north or south. But a vector quantity is a different beast. It has magnitude and direction. And this brilliantly illustrates why direction matters. Imagine holding that pen and just letting it go. It drops, right? Why? Because the gravitational force is pulling it downwards. Force is a vector because the direction, downwards, is an absolutely crucial part of the measurement. Moving right along to Section 2, Motion and Rest Explained. Now, we toss these words around every day, but in physics, they have super strict definitions. Rest literally means your position stays completely fixed as time ticks by. Think of a heavy table sitting in your room. 1 second, 10 seconds, an hour passes, it hasn't budged. It's at rest. Motion, on the flip side, means your position changes over time. If you walk from the couch to the kitchen, the clock is ticking and your position is changing. You are in motion. But here's where it gets kind of wild. Motion is completely relative. Seriously, it all depends on your perspective. Have you ever been sitting in a moving car at night, looking out the window, and it felt like the moon was chasing you? Or think about waving goodbye to a friend on a departing bus. To you, standing on the street, your friend is definitely moving away. But your friend sitting inside the bus, you look like you are the one moving backward. Motion entirely depends on who is observing and from what perspective. All right, Section 3, Distance versus Displacement. So while distance is just the total winding path you traveled, displacement is the absolute shortest, straight-line distance from where you started to where you finished. Displacement honestly doesn't care about the roads you took, the traffic you dodged, or the buildings in your way. It is simply an imaginary direct straight line connecting your initial point to your final point. Let's actually ground this with a really good anecdote from our source material. Imagine school ends, and you decide to take the scenic route home. You walk 1 kilometer to the park to hang out, then 1 kilometer to the store to grab some snacks, and finally 1 kilometer to your house. Your total distance covered is 1 plus 1 plus 1, which equals 3 kilometers. But your displacement, that's just the direct straight line from the school straight to your home. Even if there's no actual road there, that direct shortcut might only be 2 kilometers. So distance is your actual journey, displacement is the ultimate shortcut. Now, the source text throws this fantastic little challenge at us here. They call it a DCP, a Dimag Chalao problem, basically a brain power problem. So let's get your mental gears turning for a second. Based on what we just learned, is it physically possible to travel a distance but have your displacement be exactly 0? Think about it. Yes, the answer is a massive 0. No way, right? But think about it. Imagine an athlete running on a 220-meter circular track. They start at the starting line, run the entire exhausting loop, and collapse right back across that exact same starting line. Their distance covered is 220 meters. But because their initial starting point and their final finishing point are the exact same spot, the shortest straight line between them is 0. Look, I know when it comes to solving numericals on exams, people get totally terrified. But the absolutely crucial point here is that it's just 3 simple sequential steps. First, pinpoint exactly where the object started and where it ended. Second, draw a straight line between those 2 dots. Third, if that path creates a right-angled triangle, which trust me, it almost always does in these problems, just use the basic Pythagoras theorem you learned in math. A squared plus B squared equals C squared. By breaking it down visually like a puzzle, the math becomes completely harmless. Okay, let's build on that. Section 4, understanding speed and velocity. So speed just answers the question, how fast? Like a truck going 80 kilometers per hour. That's our scalar quantity. It's just a number. But velocity? Velocity answers two questions, how fast and where. If that exact same truck is moving at 80 kilometers per hour eastward, well, that is its velocity. You could literally have two trucks on the highway, both going 80 kilometers per hour. They have the exact same speed. But if one is driving east and the other is driving west, their velocities are completely different. And hey, here's a brilliant little shortcut straight from the source that'll save you so much time on exams. Physics problems love to give you speeds in kilometers per hour, but then they make you solve the math in meters per second. Instead of doing all that long, complicated math converting hours to seconds and kilometers to meters, just multiply your speed by the magic fraction 5/18. Bam! It instantly converts kilometers per hour to meters per second. Lock this visual in your memory for sure. Which brings us to section 5, uniform versus non-uniform motion. Let's look at this totally relatable analogy from our source, the Delhi road trip. So in the first hour, you're fighting through awful city traffic and you only cover 10 kilometers. In the second hour, things clear up a bit. You cover 30 kilometers. By the third hour, you finally hit the highway, like the GT Carnal Road, and you cover 40 kilometers. In the fourth hour, the road is wide open and you zoom through 60 kilometers. If you look at the time, it's ticking by in equal 1-hour intervals. But the distance you covered in each of those hours? Wildly different. And this beautifully highlights the difference between uniform and non-uniform motion. Uniform motion is perfect, it's constant, like a train covering exactly 20 kilometers every single hour without fail. Equal distance in equal time. But our road trip represents non-uniform motion. The speed was variable, we covered completely unequal distances in those equal 1-hour blocks. And let's be real, in the real world, everyday travel is rarely uniform. Variable speeds means something in our journey is actively changing. And finally, we've made it to the top of our conceptual pyramid, Section 6, Introduction to Acceleration. But first, I've got one final dimag chill-out problem for you to really test your understanding of vectors. Ready? Can your velocity change if your speed stays the exact same? Take a second. Think about the rules of a vector we talked about earlier. The answer is yes. Because remember, velocity is a combination of speed and direction. Sure, velocity changes if your speed drops, like slowing down from 100 to 60 to grab food. But importantly, imagine you're driving 30 kilometers per hour heading east, and you realize you missed your favorite roadside diner at Murphy. You take a U-turn. You are now driving 30 kilometers per hour heading west. Your speedometer didn't change, your speed stayed exactly the same, but because you flipped your direction, your velocity has drastically changed. Which brings us to the ultimate question. If we know that in the real world, motion is pretty much always non-uniform, and our velocity is constantly changing, either by hitting the brakes, pressing the gas, or taking a U-turn, how do we actually measure the rate of that change? How do we calculate exactly how fast our velocity is shifting? Well, my friends, that measurement is called acceleration. And based on the incredible foundation we just built today, you are now perfectly equipped to face that boss in our next explainer. Until then, keep questioning, keep learning, and I'll see you next time.